the material that we'll cover in Math 2000, a rather large chunk of it will be on multivariable calculus, at least the integral calculus side of things, before we start on the vector calculus. And so this particular topic that starts at chapter 7 on multiple integrals will really be the last topic that I will lecture. But you can see from the workbook, I can't remember what chapter it is. I think I might be lecturing up to about chapter 17, maybe 18, around there. So it comprises a sizable chunk of the material that we'll cover. And what's more, what we'll see in these lectures up to about chapter 17 will be developed even further by Zoltan Neufeld's lectures on vector calculus. So I think these lectures, especially today's lecture and the lectures this week, will be a solid foundation for a lot of the other material that we'll cover. Now, I'll just point out that it's worth having a look at the textbook Stewart. This is all in chapter 15. So this introduction to the so-called double integrals is in chapter 15. Now, the way I'm going to introduce it today, I mean, it's very much like the presentation in Stewart, but I like to give, with a lot of these concepts, I like to give students something tangible just before going on to the abstract definitions. And so what I'm going to start considering in order to arrive at the definition of a double integral is the problem of calculating the volume below a surface. And it's a special type of surface, or a surface in a very special form. So it's something tangible. It's something we can actually visualize, and you'll see how we'll first end up with an approximation to such a volume, and then take limits, as we do in calculus, and arrive at the definition. So just before I get into that, actually, I'll just want to remind you about something relating to the definite integral of a function of a single variable. And, I mean, you'll see why I'm talking about it here right at the start of this lecture, is because what we're going to be talking about, the double integral and its relationship with volume below a surface, is analogous to the relationship between this definite integral of a function of a single variable and the area below a curve. So let me just remind you about that definition before we look at volume below a surface. So this should all be very familiar to you, even if you've done some integral calculus in high school. This is the sort of thing you will have seen before. So in considering the area below a curve. All right, so look, just really quickly, I'm going to draw up a diagram of a curve with equation y equals f of x. Okay, so it might look something like this. And one thing you should be familiar with is that we can use the definite integral of this function. So if this is y equals f of x, so the curve is defined by that function f, we can use this function to calculate the area below this curve and above the interval on the xy axis between, say, values a and b. Or here I've just used a subscript I for interval, all right, some interval in the x direction. Okay, so what we can do first is just work out an approximation to the area. So divide this interval along the x-axis up into subintervals. So here I'll just divide it up into 3 intervals. In each subinterval, we choose a representative point. So let's say in this first interval, I'll choose this point here, and then evaluate the function at that representative point. Okay, so that corresponds to this point on the curve. And then the value of that function I'll take to be the height of a rectangle. And so the strategy is, and I can draw it in here, the strategy is, as an approximation to the area below this curve, we just work out the area of these rectangles. In this case, I've divided the interval up into 3 subintervals. So we'll approximate the area below that curve as just the area of those 3 rectangles. So in each case, I need to choose some representative point in the interval, in each subinterval, I should say. Okay, so this one, and then that's the height of the rectangle, and so our approximation to the area below that curve and above this interval in the xy plane, we can just approximate first by summing up the areas of those rectangles. Okay, so let's say these representative points I'll usually label with an asterisk in the superscript, or just refer to it as x star. And the width of these intervals are often just written as delta x. Okay, so in this equation that I've got here, we're taking a limit here. So it turns out, with this approximation to the area, if we take smaller and smaller widths of these rectangles, or equivalently take more and more rectangles, right, and in fact take the limit as the number of those rectangles goes to infinity, we end up with a better and better approximation until finally we end up with an exact value. Okay, so if we didn't have a limit here, it'd just be an approximation. But in this case, the limit is taken by taking delta x to 0, right? Or, equivalently, the number, so this n, the number of intervals, or the number of rectangles in our approximation, the limit as that goes to infinity. All right, and so what we've got in this equation here, so this difference between these two x values, those x values are just meant to be the values along the x-axis defining the intervals. Okay, so that quantity I could have just as easily referred to as delta x. Okay, so that's the base length of the rectangles, and this f of x star, okay, that is the function evaluated at our representative point in each subinterval, is just the height. Okay, so we work out the area to be the sum of these rectangles and taking the limit as the number of those rectangles goes to infinity, or equivalently as their width goes to 0. All right? So, in fact, this is how we define the area below a curve. And this is the amazing thing about the integral calculus, is the definite integral is defined as this sum. It says nothing about any connection with the antiderivative of the function, right? Where that comes into play is this very amazing and elegant theorem known as the fundamental theorem of integral calculus that relates this definition to the antiderivative of a function evaluated at the endpoints. All right, so I just want you to appreciate that subtlety. It's worth mentioning because we'll be looking at an analogous result later on. Not in this lecture, though. We'll wait till tomorrow's lecture where we see an analogue of that fundamental theorem. Okay, so I just wanted to draw your attention to that. If you remember, right, area below a curve is how we define the definite integral, but then there's this really special result known as the fundamental theorem that relates that definition to the antiderivative of a function. Okay, so just at the start of the section here, there are a few dot points, and really we're going to consider the problem of calculating, indeed defining, the volume below a surface and above some two-dimensional region in the xy plane. Okay, so essentially what we're going to be doing is defining the notion of double integral in the context of volume below a surface. In the same way, we define definite integral in terms of area below a curve. Okay, and so we'll talk about the relationship of these two concepts. And also there's a fourth dot point that I should put in here. I'll just say, I won't pose it as a question, I'll just mention the iterated integral. Okay, so I'll talk, towards the end of the lecture, I'll talk about the iterated integral. And I won't make any connection whatsoever in this lecture with the double integral, but we'll save that up for tomorrow's lecture when I'll relate the two. Okay, so that's what that's really the motivation here. So we're going to consider this problem of volume below a surface and above some region in the xy plane. We'll start by keeping it simple. Okay, so we'll start by considering only the case where the region in the xy plane is a rectangle. All right, we'll move on to more general regions in the xy plane, but just for the moment, we'll keep it simple, and we'll suppose we have a surface defined in this way, z equals some function of x and y, and now throughout all of this derivation, all of this discussion in defining the double integral, keep in mind what I've said about the definite integral of a function of a single variable. Right here we've got a curve defined by y equals f of x. Now we've got a surface defined by z equals f of x and y. Not all curves in the plane can be written in this way, y equals f of x. Right? So, I mean, for instance, the equation of a circle of radius 1 centred at the origin has equation x squared plus y squared equals 1. It's not written in that form, but more generally, we can write curves in the xy plane in the form some function of x and y equals 0, or some function of x and y equals a constant. All right, so I guess it's a special type of surface in this case that we're dealing with, right? Analogous to this situation. Okay, you can, generally speaking, surfaces can be written in the form some function of x, y, and z equals 0, or some function of x, y, and z equals a constant. But now we're just going to be considering these types of surfaces. And what's more, we'll specialise to the case where the value of this function is greater than, well, let's just say greater than 0 to start with, on this region R in the xy plane. All right, so we'll keep it simple. And now we'll ask this question: what is the volume below this surface, z equals f of x and y, and above this region R in the xy plane? All right, so keeping it simple, we'll treat R as a rectangle. So I know this, it might be a little bit difficult to see from this diagram, but in this diagram there's meant to be a surface here. And what we're interested in is calculating the calculating the volume below that surface and above this region R in the xy plane. All right? Indeed, how do we define volume? Actually, what's the definition of volume? Can anyone offer just a rough definition of volume? Not a quantitative one, but a qualitative one. What is volume? What is the volume of an object? Let's put it that way. What is the volume of a region in three-dimensional space? I could put it that way. Does anyone have any idea how we can define volume? It doesn't have to be precise. Anyone? Yeah. The space occupied by an object, exactly. Actually, let me just add to that a little bit and say the amount of space, right? And it's that word amount that we're really interested in, right? This being a maths course, okay? We're really interested in quantifying such a thing. So the amount of space occupied by that object, all right? Okay, good. So we're on the same page. We know what we're talking about, volume. So it's fair enough we can calculate something like the volume of a box, right, just by multiplying the dimensions of the box. So what, width times depth times height. All right, we can define the volume of that box just to be the product of those three quantities. But how can we then define, say, the volume of quantitatively now? How can we define the volume of an object such as this, stated in this problem? Right, volume below some surface with equation z equals f of xy and above this region in the xy plane. And this is answering that question is crucial to understanding the definition of the double integral. All right, so while later on in the course we'll move on to more abstract definitions, just when I first introduce the concept, that's what we're thinking about. Okay, volume below the surface and above a rectangle in the xy plane. All right, this is a notation that I'll use quite a lot throughout my lectures. Just using this kind of set notation, so a set of points with coordinates x and y such that x lies between a and b and y lies between c and d, where a, b, c and d are just numbers. All right, and so this is defining a rectangle now. Okay, so just over the page, this is how we're going to construct, or how we're going to get to our definition of double integral. So we'll do something very similar to what we did in the case of the definite integral of a function of a single variable. All right? Whereas in that case, from my diagram, I'll just remind you, we partitioned the interval on the x-axis up into small subintervals. What we're going to do in this case is now take our region in the xy plane and partition it up into small grid squares. All right, so these squares of dimensions, so delta x being the width of one of these grid squares in the x direction, and delta y being the depth or the width in the y direction. Okay, so here's the strategy. Here's how we're going to first get an approximation to the volume that we're talking about, to the volume under consideration. All right, so we first take our rectangle in the xy plane, superimpose a grid or a mesh, okay, and focus on one of those mesh squares. So that's this one I've got shaded in the diagram. All right, so in each square, or in this one square, what we'll do is choose a representative point, and let's give that coordinates x star and y star. All right, so they're the coordinates of this representative point. So this is just for one grid square. Okay, now what I'm going to do is evaluate the function, which is this function of two variables that defines the surface. So z equals f of x and y. I'm going to evaluate this function at that representative point. And actually the strategy here is that, so if this is the grid square, what I'm drawing here, that's the grid square in the xy plane. So I've got my representative point somewhere in there. I'm going to evaluate the function at that point, and I do apologise for my three-dimensional drawings. I'm not the most amazing artist, but hopefully, and I mean 3D pictures projected onto the page or onto the screen like this are notoriously difficult to visualise, but I promise to do my best. At least it helps with a voiceover explanation of what it is that I'm trying to communicate to you guys. So please bear with me. So at the base here, so that's corresponding to this grid square in the xy plane. And then what we're going to do is evaluate the function at our representative point with coordinates x star, y star. And so the value of the function at that point is just going to be the height of this box. And one thing I've stated at the start is, well, we're interested in quantifying the volume below that surface and above this region in the xy plane. But what we're going to do is use knowledge of how we calculate the volume of a box, right? What I was talking about, width times depth times height. All right, the value of this function at our representative point is just going to be the height of this box. All right, so there's the volume, approximately the volume below that surface and above one of these grid squares. All right, now I say approximately because when we work out the height of this box, okay, we're assuming that at the top of the box it's flat. But actually, we don't have that. What we're interested in doing is calculating the volume below some surface, which could be curved, it could have some curvature. It's not necessarily going to be flat. So hence, this is just an approximation to the volume below that surface and above this small rectangle in the xy plane. So very similar to this picture I've got on the previous page, where actually the curve y equals f of x, there's some curvature here. It doesn't quite match up with the top of this rectangle, so hence the area of that rectangle is just an approximation. So in exactly the same way, but now we're talking in 3 dimensions, does this volume of the box approximate the volume below the surface? All right, so that's just above 1 grid square. So what we do is repeat this process over all the grid squares in our region R, or in our rectangle R, in the xy plane. Okay, and so what we end up with, an approximation to the volume of one of these boxes, an approximation to the volume below the surface and above one of these grid squares, where the value of the function at the representative point with coordinates x star, y star, is just the height of the box. And this delta A is just the base area. Okay, but we repeat this process over all the grid squares. So in this diagram in the xy plane, remember, we've partitioned the rectangle up into grids. Okay, and we repeat this process and then just sum up the volumes of the individual boxes. And this is going to give us an approximation only, right? It's going to give us an approximation to the volume below the surface that we want. So the strategy here is we take smaller and smaller grid squares. We get a better and better approximation. Finally, we take the limit as the base area of those grid squares goes to 0, and we end up with an exact expression for the volume below the surface. And this is what we're going to define to be the double integral. All right, I might actually make reference to some pages in Stewart, some very specific pages, and one example in particular. So I'll say see Stewart on the textbook, pages 998 to 1001, and there's an example. I think it's just called example 1, which is on page 1001, that that works through this calculation. For one example, in fact, I've got a copy here of one of the pages, so I just want to make sure I'm clear about this, so there are no copyright issues or anything like that. This is from the book Calculus, edition 6, by James Stewart, page 990. And in fact, this is exactly the same example that I'm referring to on page 1001. But I just want to show you the pictures, right, what I'm referring to. So the problem under consideration here is the volume below this paraboloid with equation z equals 16 minus x squared minus 2y squared. I don't know if you can see it there. First, they start off, let me just scroll down, partitioning, the volume below that surface and above a rectangle in the xy plane. They start with an approximation using 4 rectangles, then an approximation using 16, and so on, increasing the number of grid squares, making them smaller and smaller. And what I want to show you is that as it gets smaller, you can see that actually this seems to be converging to the actual volume that we're interested in. Okay, that is the volume below this surface for this example, and above that region. So in each case, I think I've highlighted the numbers there. So for 16 blocks, it's 41.5, then 44.8 something, then 46.4 something. The approximation is getting better and better, but until finally we take the limit as as the size of these boxes, or in other words, the limit as delta A goes to 0. To further demonstrate this point, I've brought along a little stage prop here. It's a nice little toy. Some of you might have seen it. I think it's referred to as pin art. So it's this little thing. It's got hundreds of pins in here, and you can tip it back, and so the image stays behind. So why on earth did I bring along this to a lecture on double integrals? Well, hopefully you can see the connection. Ooh, doesn't like that. Hopefully you can see the connection between this this little toy and double integrals. So let me just maybe put it up on the screen, just so you can see the sort of thing I'm talking about. If I had a surface... Oh no, it doesn't really come out well, does it? If I had a surface here, say defined by my arm or part of my hand here, I could approximate the volume below that surface by calculating the volume of each of those little pins and then adding them up. Hopefully you get the idea. Look, it's not very... I can appreciate that didn't really work. What I might do is pass this around for you to have a look at during the lecture. So a couple of things, I mean, some nice stories about this. I've had this toy for years. I remember once, a couple of years ago, I keep it in my office, right? A couple of years ago, some students came in during my consultation and made a rude gesture on it and left it facing my door. So other people would come in, and there I was saying, "Oh, welcome, come on in," with this welcoming sign on the thing. Of course, there's my favourite, Fight the Power, which is this one, the raised fist. Also, while I'll pass it around and you guys can play with it, just one word of warning. Tempting as it may be to put it on your face and tip it back, I've lived in a lot of share houses over the years. I mean, this was years ago. This is going back, right? And, you know, we've had parties. It gets passed around. I make absolutely no guarantees of where that thing has been. All right? So just consider that before you put it up to your face. And anyway, so look, as you pass it around, I mean, keep in mind the point I'm trying to make here. Okay? Keep in mind the point I'm trying to make about first approximating the volume below a surface. All right? And so I think these pictures that I've got up here from Stuart demonstrate the idea nicely, and there's also the pin art demonstration. So over the page, there's just one little detail we've got left. There's one small detail. At the moment, we've just got an approximation to the volume. What is the volume? What is the exact volume? Or indeed, how do we define the volume below the surface? Well, I've pretty much summarised what the strategy is here. So we've worked out an approximation so far. So the next step is just to say, well, we let delta x. So by the way, in this diagram, where's that previous page I had up? Oh, it's just below. So remember, delta x, so given one grid square, delta x is just the change in the x direction, or the width in the x direction. Delta y is just the width in the y direction. So if we let delta x and delta y simultaneously go to 0, or equivalently, I could say, if we take the limit as delta A goes to 0, or say these numbers m and n go to infinity, where m and n are just the number. I mean, this is all outlined in the text on page 50, but where m and n are just the number of intervals along the x and y axes respectively. okay, we end up defining the volume. All right, remember, we're all about quantities here. This is a maths course. We're all about quantities. We end up defining the volume. So now we've got an equal sign here, defining the volume to be the limit as either one of these limits are obtained of this expression. This is what's called a double Riemann sum. Okay, so remember, this f of x star y star is just the height of those boxes, and the delta A is the base width. All right, and we're taking the limit as the base, the base area, I should say. We're taking the limit as the base area goes to 0, right, in one of these ways. So if this limit exists, it's not always going to exist, but if it does, we write this in this way. So we use two integral signs standing next to each other, and we put a subscript on those, much like I did in that very first definite integral I put up on page 49. I've got a subscript I there, an I for the interval. In this case, the subscript is the R, which is just the region in the xy plane. In this case, we kept it simple. It's just the rectangle, right? So later on, we'll consider more complicated regions in the xy plane. All right. So if that limit exists, right, it's not always going to exist, but if it does, we call the function f integrable. All right, one example of an integrable function is a continuous function. So every continuous function is integrable, although the converse is not necessarily true. But nevertheless, this is what we call the double integral. All right, so what we've ended up doing is, or what we've done is consider the problem of defining the volume below a surface of the form z equals f of x and y and above some region in the xy plane, and we've arrived at the double integral in much the same way as we did for the definite integral of a function of a single variable and the problem of the area under a curve. Okay, so can everyone see the analogy between those two concepts? And I hope everyone understands, or at least gets the idea about this definition. All right, so that's the double integral. Now, of course, there is one problem, and that is, given a function and given a region, or given a rectangle, we've only considered rectangles, so given a function f and a rectangle, how do we evaluate that double integral? So do you mean to say each time we have to go ahead and work out go through that construction, work out the double Riemann sum, take limits? Well, actually, there is good news, and this is going to be the topic of tomorrow's lecture. And that is actually how we evaluate double integrals. There's very good news in much the same way as the fundamental theorem of integral calculus was good news, relating the antiderivative to the area under a curve, okay, to the definite integral. Now, it turns out there are some properties of the double integral that are worth mentioning, and I'll be coming back to these throughout the subsequent lectures, just a few properties that are worth mentioning. So just to explain my shorthand, so here, where I've written f and g, I should have really written f of xy and g of xy, okay, as being some integrable function, so assuming the double integral exists. And so now that I've introduced the double integral, by the way, these are abstract properties, all right? These properties are not just for volume below a surface, but now that I've constructed the double integral using, or in the context of volume below a surface and above a region in the xy plane, all of these properties you can try and visualize in terms of volume, all right, just to help you understand them. And so if you think about these, what these properties are saying in terms of volume below a surface, it's just saying that, all right, if we take the sum or difference of these, the values of these functions over some region in the xy plane, then that's the same as taking the sum or difference of the double integrals of the individual functions. And think of that in terms of volume below a surface, right? It all makes sense. The property's additive, right? Basically, these first two properties are telling us that the double integral is linear. All right, so in the sense that if c is a constant, I should say that as well. I should say that explicitly. If c is a constant, then the double integral of a constant times a function of x and y is just the constant times that double integral. All right, this third property requires a little bit of explanation. So on the left-hand side, I've got double integral over some region R, whereas on the right-hand side, I've got the sum of two double integrals, one over R1 and one over R2. So let me just clarify that in this case. The region R that appears in the subscript on the left-hand side is understood to be the disjoint union of these two regions, R1 and R2. So I should say the disjoint union. What does that mean? Well, if I take the intersection of R1 and R2, this is empty, or they only touch on the boundary. Right, they only coincide, I'll say, or only boundary points of the two regions. Okay, so that's understood here, and actually this property number 3 is something that we will use a lot when we come to look at working with the double integral over more general regions. Okay, and finally, property number 4 is, again, thinking of this in terms of volume, it really makes sense, right? It's really quite intuitive, is that if the value of the function f is always greater than or equal to the value of the function g over some region R, then the value of the double integrals is also the same. Okay, so that kind of makes sense intuitively if you think of it in terms of volume. All right, so that's the definition of double integral, right? Defined in much the same way as we define the definition, as we define the definite integral of a function of a single variable. Okay, but there's one thing that's still outstanding, is how can we evaluate those? What is the analogue of the fundamental theorem of integral calculus? How can we evaluate these double integrals in a useful way, in a practical way, and what connection, if any, does it have to do with antiderivatives? All right, I'm actually not going to make that connection in today's lecture. That's the topic of tomorrow's lecture. The result is actually known as Fubini's theorem. I'm going to be talking about that in tomorrow's lecture. But before we get there, there is still some time to talk about iterated integrals, what are called iterated integrals. So this is the additional dot point that I put at the top of, at the start of that, of the lecture, right? Iterated integrals. Now, at this stage, I just want to be clear about this. I'm not making any connection whatsoever between double integrals and iterated integrals. At this stage, all I want to do, now that I've defined the double integral, let's push that aside, and now I want to define what's called an iterated integral. And we'll make this connection, we'll connect the two tomorrow. All right, so now this is quite straightforward to define, the iterated integral. So say we come across an expression like this, where we've got a function of two variables, x and y, and we have just a single integral sign with a dy here. So that means what we're going to do is differentiate the function f of x and y partially with respect to y, and then evaluate it at y equals c and y equals d, right? In much the same way as we evaluate a definite integral of a function of a single variable. And in this expression, it's understood that we're treating the variable x as constant. All right? So just keep that in mind. All right? So that when we work out this this integral, right? We work out this antiderivative. or anti-partial derivative, maybe I should call it, and we evaluate y at these two numbers, c and d, we're just left with a function of x only. Okay, so what's more, we can also take that function of x and talk about the integral of that function with respect to x, evaluated between x equals a and x equals b. All right, and so now substituting this into the expression for a, what we end up with is just what's called an iterated integral. Right, we end up with this expression where we first integrate the two-variable function partially with respect to y, evaluate it at those two values for y, and then integrate the remaining function, with, which is a function of x only, integrate that with respect to x. So it's called an iterated integral. We work from the inside out. Let's just work through a very simple example just to establish exactly what we mean. Okay, so in this case, we're integrating the function x squared y. So remember, it's an iterated integral. So this means we evaluate from the inside out. So we start by integrating. So I'll just say we evaluate the integral with respect to y first. Okay, so we've got integral from 0 to 2 dx, and all of this next line is happening inside this integrand. All right, so we integrate x squared y partially with respect to y. So that'll just integrate to a half x squared y squared. And then that's evaluated from y equals 1 to y equals 3. So we're just treating x as a constant and treating the integral with respect to y just like a definite integral of one variable. Okay, so now, again, this is all happening inside this, this integral from 0 to 2 with respect to x. Now I evaluate at those endpoints. So remember, we substitute in y equals 3 first. So we end up with, so we've got a y squared, so that's 3 squared, which is 9 over 2 times x squared, minus the value obtained when we substitute in the lower bound, which is just y equals 1. So minus a half x squared. All right, and then that simplifies to, so again, this is all happening inside this integral with respect to x. So 9 over 2 minus 1 over 2 is 8 over 2, which is 4. So we end up with integral of 4x squared. So now it's just a definite integral of a function of x. Okay, so this is just 4/3 x cubed, evaluated from x equals 0 to x equals 2, which is 4/3 times 8, 32 on 3. Okay, so that's another thing to point out. This iterated integral evaluates to a number. In this case, all the bounds are numbers. In particular, the bounds of the outer integral with respect to x were just the numbers 0 and 2. So I should expect, when I work through that iterated integration, working from the inside out, I should expect to get a number. All right, but it turns out, because we've got functions of two variables, it turns out there are two possible orders of integration, right? So here I've first integrated with respect to y and then with respect to x. So what if we did it the other way around? All right, so here's the exact same problem, but now integrating first with respect to x, then with respect to y. And look, I've changed the bounds as well. So in the previous example, the bounds for y were 1 and 3, and the bounds for x were 0 and 2. So I've actually switched the bounds as well. All right, so working from the inside out, so this is going to be equal to the integral with respect to y from 1 to 3. So that first integral with respect to x, so this entire calculation is all happening inside the integrand with respect to y. Okay, so integrating this with respect to x, we end up with 1/3 x cubed y, evaluated from x equals 0 to x equals 2. Alright, so remember I treat y as a constant here, so think of it as partial integration. So this is then, well, actually let me just write round bracket. So we've got substituting in the upper bound, we'll have 2 cubed, which is 8. So that's 8 on 3y minus the value obtained when we substitute that lower bound, which is just 0. Alright, so now we've just got this integral with respect to y from y equals 1 to y equals 3. So now it's just a definite integral of a function of a single variable. So that's just 4/3 y squared evaluated from y equals 1 to y equals 3. Okay, so that's just 4/3 times 3 squared is 9 minus 1 squared is 1. And again we get 4/3 times 8, or 32 on 3, and which I'll just finish by observing that, which is the same value obtained on page 52. Okay, so we'll explore this connection in tomorrow's lecture. Actually, it comes as no surprise. It will come as no surprise that these iterated integrals are intimately connected to the double integral. And in fact, what we've just done in this calculation is work out the volume of this three-dimensional object, the volume below that surface and above the rectangle, defined by x between 0 and 2 and y between 1 and 3. Okay guys, see you tomorrow.